So, let me continue today showing a little easier method. One of you already pointed out that we do not need to write those matrices to find which irreps the molecular vibrations belong to. Okay. So, I thought let me just brief you on that before we get on to Lie groups. Okay. So, whatever we did, I hope you remember, we went through an elaborate exercise for a nonlinear triatomic molecule where two of the masses were identical. One of the mass was capital M and the other two was small m. It is exactly like the water molecule. And to find the reducible representation for all molecular motions, including translation, rotations, everything, you put in 3 degrees of freedom for every atom in that molecule. Clear? So, all these atoms will have 3 Cartesian coordinates and we need to work out the reducible representation or characters for the reducible representation, which can account for all the molecular motions. Okay. So, to do that, what we can do is, we did this tensor product of states and so on. We do not need to really do that. What we have to remember is, if you do an identity operation on this molecule, each atom remains in its own place, right. So, each atom remains in its own place. So, you will have character for each atom. You know, if you add up all the 9 degrees of freedom, you will get the character associated with the identity element to be 9. Okay. So, that is what you will get. But if you want to do rotation by an angle theta, I am taking theta to be arbitrary, which will be different for different groups, but discrete value. Okay. So, if you take rotation by theta, you know the x, y and z coordinate for every atom will undergo this transformation. Okay. So, if you take this and try to find the trace, if you write this matrix which does this transformation, the trace will give you 2 cos theta, right, and there will be a 1 for the ZA. So, it is exactly 1 plus 2 cos theta for an atom in the molecule. If there are NC atoms which are not displaced, okay. So, in this particular example, when you do a C2 rotation, what happens? These 2 atoms get displaced. Okay. The number of atoms which do not get displaced is just 1. So, the NC will be 1 in that case. Okay. So, if NC atoms are not displaced under rotation, then the contribution to the character will be NC multiplied by the character which is the trace of the 3 by 3 matrix, which is 1 plus 2 cos theta. Is this clear to you? So, one oxygen atom is unmoved under C2 operation and you are doing C2, C2 means theta will be pi, right. So, cos pi is minus 1, minus 2 plus 1 will be minus 1 and NC is 1. Is that clear? So, that will be the character. Identity operation of course is identity matrix for each of the atoms. So, the trace of that matrix will be 9. C2 operation for a general theta operation Cn, where theta is 2 pi by n, this is the formula where Nc is the number of atoms which are not displaced under such a operation. So, using that, because NC is 1 here and C2 is only a 180 degree rotation, we get the character associated with the C2 operation for this nonlinear molecule is -1. Okay. I am not writing matrix representation, I am just directly writing the molecular motion of this molecule, what should be the character for a reducible representation. I am not even writing the matrix form. Is that clear? So, let us do the same thing for the other two elements also. If n sigma atoms are in the reflection plane, then character is just n sigma. Okay. So, suppose you take this to be the xz plane, which we were discussing in the lecture. All the 3 atoms are in the xz plane. So, if you do a reflection in the xz plane, 3 atoms are there. So, n sigma is 3. So, the character will be 3. Okay. You can prove it rigorously, but I am giving you a final answer. So, therefore, the character for the molecular motion reducible representation is going to be 3 for reflection in the xz. What will happen for the yz plane? Can somebody tell me? 1? Oxygen is in the yz plane. Yeah. So, the character for reflection in the yz plane is again 1. Okay. So, you write this out. Once you do this, the rest of the steps follows. Given a reducible representation of a molecule with 3 n atoms, you know how to do the decomposition into irreducible representation, and you find that there are totally 9 modes of motion, right. 3 one dimensional irrep, 1 one dimensional irrep, 3 plus 1 is 4, and everything is one dimensional. Why? It is a C2V symmetry. The molecule has a C2V symmetry. It is an abelian group. So, all the irreps have to be one dimensional, and all the motions should add up to give you the total degree of freedom. So, 3 into 3 is 9 degrees of freedom, and this 9 breaks up into linear combination of this. Breaking I have not worked it out here, but we have done enough exercise problems that given a reducible representation with this character, you should be able to work out the irreps into which it can decompose. Okay. So, this part I am not doing, but you need to do this. Okay. Any questions? 9 for? Because see, finally I am going to take these as the degrees of freedom, right. X, Y, Z for atom A, X, Y, Z for atom B, X, Y, Z for atom C. So, when you do an identity operation, X, Y, Z will go to X, Y, Z. Okay. So, 3 times 3, which will be 9. Is that right? So, you can put even here theta to be 0 if you want. In this expression which I have written, you can take theta to be 0. If you do that, then you will get 3 and 3 are unchanged, 3 into 3 is 9. Is that clear? Yeah. Any other question? So, once we have this, we have the 9 modes of vibrations, sorry, 9 modes includes translation, rotations and vibrations. Okay. So, this splitting which I have done here, in order to do this, you do not need to write the matrix representation to do this. You can do this argument to actually figure out how many vibrational modes are going to be one dimensional. That means that frequency will occur only once. If suppose you had another group like C3V, the way I have given it in the assignment, if it belongs to a 2 dimensional irrep, then you can, looking at it, you can say that experimentally if they start looking at the spectra, they will see degenerate frequency. They will see 2 spikes with the same frequency. Okay. So, these are things which you can guess by just working out with the group set. Is that clear? So, in this C2V case, you have each irrep to be one dimensional. So, each frequency has to be distinct. Did you work it out? Sachin was supposed to do the discriminant, no? Frequencies are different or? Very good. So, why is it different? Now you know it has to be different because it is 1D reps. So, none of the frequencies can be degenerate. If you find the eigenvectors and 2 eigenvectors shares the same frequency, eigenvectors are very big, not simple. I see. Maybe you can show it to me and I will simplify it to you. Okay, fine. Okay, so what I want is this we have already done. Once we have broken it up into this irreps, then you have to subtract out. What I did last time was I treated it as if we are in the 2D plane. Now I have just taken it, someone was saying is it important to work in 2D. So, now today I am showing that even if you work in 3D you will get back the same vibrational modes. That is all I am trying to justify by using this shortcut way of writing the characters for the reducible representation. Okay. So, 3D, if you take the motion to be in 3D, you will have 3 into 3 which is 9 degrees of freedom to start with. Earlier when we were doing, we were taking it as a 2D and then I said 2 into 3 which is 6 degrees of freedom. So, that is the way we started with. Okay. So, here I am doing it as if it is a 3D situation and then you have to remove the translation and the same procedure there we did only the translation along x and y we subtracted, but now you have to also subtract the translation in the z coordinate because we are doing it like a 3D problem. Okay. So, associated with the z, associated with translation along z, you will have an A1 which should get removed. Okay. Associated with x translation, you have to remove one B1 and similarly y translation will remove one B2 out. Okay. So, essentially it becomes 2A1 plus A2 plus 2B1 plus B2. Is that clear? This is after we have removed the translation in the x, y and z direction. Okay. So, now what we are left with is whatever we have got after subtracting the translation is the rotational irreps plus the vibrational irreps. Okay. So, now I have to remove the rotational irreps out of this. Then what will remain will be the vibrational modes. So, rotations you can see about z axis is A2, about y axis is B1, x axis is B2. Okay. So, I need to subtract them. So, once I do that, I get the, I probably missed out, there is a B1 rotation and what happened? A2, B1. So, the answer will be, there should be 3 rotations, no? What happened? Huh? Louder? Did I miss something, some factor? So, it is 1 A2 and then the B2 will also get removed, okay. B2 will get removed and 1 B1 will get removed, okay. Excellent. So, what we have essentially, irrespective of whether we looked at it as a 2D problem or a 3D problem, the vibrational degrees of freedom should have to be 3 and the irreps which it belongs to will not change. Okay. We did this in a long process. One was using the normal coordinates and the other process where I said let us look at it as a tensor product of 3 atoms with xy coordinates. There also we got 2a1 plus b1. Now I have shown you by doing it as if it is a 3D problem, still we get the vibrational modes to belong to irreps 2a1 plus b1. Is that clear? Okay. So, this anyway I have worked it out for you, the projectors and basis states in 2D, you can try to redo it for the 3D case. Okay. Just as an exercise, you can write the matrix representations for the reducible one which I have here. For this case, you can work out the matrix representation, find the projectors, subtract out the projectors for translations. You can do that elaborately. Here again you will start getting a similar expressions. Okay. It is tedious, but it is straightforward. Okay. That is why when I did it in the class last time, I just confined to as if it is constrained to move on a plane, and then it became a little simpler. Okay, so I have not really discussed if you had rotoreflection operation, okay, what happens to the contribution to the character. I will leave it to you to try it out and see what happens when you do a rotoreflection. If NS atoms are not displaced under rotoreflection, then what is the contribution to the character? Okay. That is one I will leave it to you, and if you use those information for rotation which I have already discussed, you could actually work out the character for the molecular motion of, let us say, a molecule with TD symmetry. Okay. Which molecule has a TD symmetry? Tetrahedral. Methane has this, which we saw in the video. So, there you could also do one more stuff that you can directly. So, the way I wrote here, so I said NC atom with 1 plus 2 cos theta is the character for a reducible representation for a specific rotation which you are doing. Okay. What you could do is that you can also remove the translation of a molecule . That will be one, the character for that, character for translation is 1 plus 2 cos theta. Again you can write character for rotation, you can take Rx, Ry, Rz basis, how it transforms under rotation. It will transform exactly like your position coordinates. Rotations are proper transformations, right. If you take Rx, Ry, Rz, the operation which you are going to do will give you Rx prime, Ry prime, Rz prime, right. What will that be? Any change or same? still the same 1 plus 2 cos theta. Okay. So, you could try and remove reflections, do not add to your translation or rotations. Okay. So, instead of the earlier one where we wrote the gamma reducible wrote this as 9 minus 1, 1 was 3 and the other one was 1, right, or the other way round. This was 3, right. You could write the vibration alone, reducible representation for vibration alone. So, there you can try and remove these two. So, if you try to do that, chi vibration for rotation by theta will be NC minus translation minus rotation. So, it will be NC minus 2, okay. That will be the expression for the vibrational. It will only look at the vibrational degrees of freedom. Okay. So, what will that be? So, for theta equal to 0, all the 3 atoms, 3 minus 2 is 1, 1 into 3, that will give you directly 3, and you know vibrational degrees of freedom are 3. Identity matrix has to be a 3 cross 3 identity matrix, it has to be 3. And what about this? That had 1 atom, right. This 1 atom, when you do a theta rotation on the H2O molecule, oxygen, hydrogen, hydrogen, when you do a C2 rotation about z axis, these two get displaced, okay, only 1 atom is undisplaced. So, NC has to be 1 minus 2 and then 1 plus 2 into cos 180 degrees, because I am doing a C2 operation, right. So, what will that be? Minus 1. So, this is plus 1 finally. These things will not change, okay, fine. And now you can use the character table to see how the gamma vibration, I am claiming that it will be twice A1 plus B1, okay. Okay, but I want you to check it out. Okay, please check it. So, this is the only non-trivial operation in the water molecule, but if you go to the methane molecule, you have other operations. You can do a rotoreflection. You can do a rotation by 90 degrees and then do a reflection, right. If you have seen those slides and played on this animation, you will see that you do have a rotoreflection. So, this character table, when you start doing, I also want you to check how the under rotoreflection the characters change, how the characters change, I want you to fix it. Just like this expression, this is for rotations. For rotoreflection, I am going to call it as S theta. I want you to find out if NS atoms are undisplaced under rotoreflection, what will be this factor? I will leave it you to check it out. And once you know that, you can again play around. Also, rotoreflection, you will have translations and rotations to be removed out of it. Okay. Rotoreflection has a rotation component in it, unlike your reflection alone. Okay. So, you have to remove those degrees of freedom, and if you write down the vibrational degrees of freedom, the character for that, how many will be there in methane molecule? 5 atoms, 5 into 3 is 15, 15 minus 6 is 9 vibrational degrees. So, the identity element has to be 9, which is true here. You can see that the NC, which is this NC minus 2 will be 5 minus 2, which is 3. 3 into 3 is 9 for theta equal to 0. Okay. So, that is why the identity element is 9. Rotation by 120 degrees, cos theta will be half, minus half. So, this gives you a minus 1 and a plus 1, this will become 0. Is that clear? You all with me? So, that is why the character for when you consider the C3 operation turns out to be 0. C2, you can check it out how the C2 axis is fixed on the TD plane, okay, and see which atoms are getting displaced, which atoms are not getting displaced, okay, and then you can figure it out that this is 1. For the rotor reflection I have not really worked it out for you, but I want you to first do that and then you can figure that out, it is minus 1. After you have written this, writing this down is very straightforward. You know how to find the number of times in a reducible representation each irrep occurs. For that you need the character table, and using the character table you can fix it. But what do we observe from this final answer? There are the vibrational degrees of freedom will have one non-degenerate frequency, 2 degenerate frequency, 2 types of 3-fold degeneracy. Is that clear? This is the interpretation. You have totally 9 vibrational modes, but the number of frequencies are only 4 distinct frequencies in this case. In the water molecule all the frequencies were distinct, but here I am not finding the frequencies, but I can at least tell an experimentalist, if you are going to make these atoms interact with the electromagnetic field of certain frequency, you start seeing spectra and you will be able to see that spectra. From there they can find what is that frequency, and you can tell them that you should be able to get 2-fold degenerate, you should be able to get 3-fold degenerate. Okay. I am not doing anything other than using only the tools of great orthogonality theory and of course the symmetry of the molecule. Okay. So, this is what you saw in that video today. Maybe you can go and replay it again and see. In the methane molecule they say that you have 3 different vibrations which has the same frequency, they can superpose and you get a superposed mode of all those frequencies. Is that clear? Interesting, you know, I just want you to appreciate the fact that this is really use this information to write the net vibrational representation in TD, which I have not worked it out here, but please try it out.